Consider the following nuclear reaction that uses deuterium and tritium as fuel. We have hydrogen 2, hydrogen 3, and they go to helium 4. Okay, complete the reaction. What is the name of the new particle released during the reaction? All right, so the way we're going to do this is we're going to do a conservation of nucleons, the protons and neutrons. So here is the sum. This is the atomic mass of the isotope. So, and this is the number of protons. So we know here that we have 1, 2, 3, 4, 5 neutrons plus protons. And then we have a total of 2 protons. So I'm going to rewrite this here as helium 4. I just prefer it over there. It's all the same. And so then we're going to have a mystery particle. So we have 1, 2, that's satisfied. So we're going to add 0. And then 1, 2, 3, 4, 5, 4, we have 1. And we have 0 protons, but all the neutrons plus protons added together is 1. That's just going to give us 1 neutron. And then I'm going to put a little gamma here just for energy. And that's just going to be an assumption, not needed. Just makes me feel good. So now, complete what is the name of the new particle released. So this is a neutron. This is an alpha particle. And then there's probably electrons, which I left off. Determine the mass defect of a single reaction, given the following information. All right, and then they give us the mass of all these atoms in atomic mass units. And so the idea here is the mass of an atom is not equal to the sum of all its component parts. Therefore, there's going to be what's called they say mass defect? Mass defect. That mass defect is going to be the energy released. So if we look at this as 2, 1 hydrogen plus 3, 1 hydrogen goes to 4, 2 helium plus 1, 0 neutron, we can add up these masses here. So this one is going to be 4.0026. This is going to be 1.087. And when we add those together, we get 5.0113. And then when we add these together, we get 5.030149. And sig figs, these are kind of challenging because usually what I do is I just take as many digits as I have available. It's the sort of thing where since you're taking a difference of 2 numbers that are very close together, you usually get a pretty small number. So for this, we're going to find the mass defect is equal to 0.018849. And this is atomic mass units. So here, we can now determine the mass defect. Bam, right there. Got it. Excellent. Determine the energy in joules released during a single fusion reaction. All right. So what we're going to do is we're going to convert this over to energy. And they asked us to do it in joules. So we're going to say that energy equals mc squared. Our mass is going to be 0.018849 atomic mass units. And we want to convert this over to joules. So we'll do Wolfram alpha. Let's look at AMU to kilograms. And 1 AMU is 1.66 times 10 to the negative 27th kilograms. So it's going to be 1.66 times 10 to the negative 27th kilograms, very small, per AMU. And that gives us atomic mass units. Or this gives us mass. And then I'm just going to use 3 times 10 to the 8th for the speed of light. And that's going to be in meters per second. That's going to be quantity squared. So going back to Wolfram, we will do 0.018849 times 1.66 times 10 to the negative 27th times 3 I'll do quantity. 3 times 10 to the 8th quantity squared. And I get a small number. Yes, seems reasonable because it's just one fusion. 2 lonely atoms come together and fusion. Not a lot of energy. Especially in terms of, well, it's a lot of energy relatively. All right, 2.816 times 10 to the negative 12th joules. And then determine the energy in joules. Check. Kathmandu city requires 10 to the 20th joules per year to meet its energy needs. How many single reactions would be necessary to provide this magnitude of energy? All right, so we have 10 to the 20th joules. 10 to the 20th joules per year. And we want to cancel out joules, so we have 2.816 times 10 to the negative 12th joules per reaction. And so this is going to give us, go over to Wolfram, we'll do 10 to the 20th divided by our previous answer. And that gives us, okay. 3.55 times 10 to the 31st. 3.55 times 10 to the 31st. 3.55 times 10 to the 31st reactions. So that is, Kathmandu requires 10 to 20 joules per year to meet its energy needs. How many single reactions would be necessary to provide this magnitude of energy? And that would be 3.55 times 10 to the 31st reactions. So hope that helped, and see you next time.